Hi, hello everyone. Great to be here. Today we'll talk about BinWhisper, our language model-based tool that automatically finds vulnerabilities on Samsung phones. I will cover the motivation, the design, and some real bugs it found. I will also leave the sufficient time for a Q&A. So this is a small team. I'm Chirandai. My research mainly focuses on the finding vulnerability and writing exploits. And Ifeshi is my collaborator on this project. She's currently an undergraduate student and interested in finding vulnerabilities using AI. And she developed this tool under my guidance. So large language models are becoming an essential tool for anyone who writes codes these days. I use ChatGPT and Cursor almost every day, and about half of the lines come to AI directly. And due to large language models' excellent performance, security teams are integrating large language models into their workflows, static analysis, penetration testing, bug patches, and so on. And some pioneers are pushing even harder. Google Project Zero and Reliance research have shown that the large language model can find bugs in real-world projects like the Linux kernel. And our own research kicked off around the same time as Google, and the result? Yeah, it helped us achieve the Hall of Fame in the Samsung Mobile Security 2024. And we believe all of these facts have shown that large language model for security could be the future trend to the community. And here's the plan for the next. First, I will walk through a bug we found by hand, and will show the detailed steps of the auditing journey. Next, I will show the large language model strengths in code review. Then I will explain how we combine human expertise with large language models into one pipeline to discover the bugs in binary files. And finally, I will share some bugs that our tools found and show the model's reasoning steps so you can see how it reached high confidence results. First, let's dive into the CVE. So last year, we successfully exploited this bug and achieved a RCE on Samsung phones. And this function parses RTCP app packets from the remote. The bug is a single M copy that trusts the length parameter, and this field is fully controlled by the attacker, and its type is a word, so it could be up to hex FFFF. So both the source and destination buffers are much smaller. The bug looks simple, but reaching this point took hard work. We had to trace the call stacks and analyze the data structures across different modules to verify this OB size. And in theory, checking a buffer overflow is simple. Find where the buffer is allocated, record its exercise size, and review every memory exercise to it. But in practice, it's a heavy work. Even with full source code, you may spend days figuring out the classes and pointers relationship. So given the stripped binaries, it gets harder. So comments, type names, and symbols are gone. You have to do reverse engineering, track offsets by hand, resolving indirect calls, and using the debugger to verify the data structures in the raw base. And these reconstruction jobs often take longer than proving a bug. And this page shows the entire call stack and the data structure of this bug. So first, the C transport manager start receive starts the packet receive logic. Then the RTP create function, it allocates the primary RTP context, and the sock notify function invokes the callback functions when an RTCP packet arrives. Then the two functions are the RTCP core handle routines. Then the following functions start to parse the RTCP packets. I highlighted some important pointers accordingly to show the relationships among the complex data structures. The same color indicates that the pointers are pointing to the same buffer. All above has shown what we did to find the bug. Well, auditing the code, none of these steps are really hard, but they are time-consuming. And that's what inspired us to have a large language model handle this part instead of us. So until last year, vulnerability hunting was almost a human-only work. Experts disclose the attack surface, reverse binaries, and try to find bugs with hardcore techniques. And early chatbots hallucinated too often to trust for critical analysis or reasoning. However, things have changed. New reasoning models from OpenAI and other vendors can now handle longer contexts and show precise reasoning steps. And like a human expert, a large language model can be copied and run in parallel. So with a clear pipeline and prompts, they can read code at a fast speed and never need a break. Let's see where the large language models help most in code reasoning. This page shows how a large language model reads code. So we use an ADA plugin, Geppetto, isolate the vulnerable function from the previous bug, and use the built-in prompts, explain this function, and remove the variables. Now compare the before and after. The model assigns clear names, infers each variable's role, and adds a short summary. Then the code becomes easy to review. Then I pasted the vulnerable function to the chatbot and asked, is it vulnerable and why? So it returned 3 points. One matched the real bug, and the other 2 were false alarms because of the simple prompt. However, even the correct answer added a maybe condition. If the app data length is large enough, my copy may overflow. And that's not helpful. As we all know, big sizes can make overflow. So here's the problem. When you are auditing hundreds of functions, you need firm yes or no answers, not maybes that still need further triage. So the solution is straightforward. Give large language models enough and clear preconditions, then the large language models act like a set solver, take conditions and concrete data, then output precise answers. For example, if we state the return value is 1024 bytes, the RTCP packet buffer is 1600 bytes, and app data length is an attacker-controlled 16-bit field, then the model will flag the overflow with high confidence. And someone may say it looks too deliberate or artificial, but this introduces the necessary step, data structures reconstruction. So using the journey of how we found the CVE 2024-34587 as a case study, I will show how data structure reconstruction makes our large language models analysis precise on stripped ARM64 binaries. And this is our tool's architecture, and it has a core controller, environment interfaces on the right that interact with the binaries, and mobile device, and human, and agents on the left handling different tasks. So it might look familiar, and I had the same reaction when I saw Project Zero's Project Net 10. And they have also have the large language model backend, agent, controller, and tool site. But the key difference is Project Zero works at the source code level, and we are working on the 6 stripped ARM64 binaries. That forces us to do additional reverse engineering works and have a different solution. So we feed a bunch of .so files into a decompiler equipped with our own custom plugins. Then we attach the FRIDA to a real device to resolve indirect calls and verify memory layouts. Once we have all necessary data, our large language model agents take over. They find the packet receive and parse routines, tramps the global call graph, reconstructs the data structures, and performs the vulnerability analysis. And here's our roadmap. Human does only 2 things: pick the target process at the very beginning and verify the results at the end. Everything between is taken over by the agents. So the first, identify the target process. Last year, I shared how we exploited bugs in the Stack Video Engine service. So the service has the following features we are interested in. It runs on a Hyper-Bridge. It can be accessed from remote directly, and it is installed and runs by default on the Samsung phones. And its triggering condition is simple, just need a package center. So these features contribute to the higher value of bugs found in the Stack Video Engine service. And we didn't build a fuzzing harness for this service because the code base is small. So the cost to design and maintain a harness won't pay off. After we evaluated the real workload, a large language model-based auditing tool was a better try. So the tool decompiles the targets and builds a global call graph that every later step depends on. The decompiler produces readable pseudocodes so that the large language models can index and review. And to resolve the problem that static analysis would break on indirect calls, we take a practical method, run the app, attach Frida, hook every indirect call, and read the real jump from the register. Next, locating the packet receive and parse routines in our attack scenario is important because the receive routines represent the attack surface and disclose how to interact with this service. And the parse routines are where the bugs often appear. These functions are easy to spot. For example, like have function name, like RCCP receive packet, or have a big switch statement, or a nested if or else statements in the code on magic numbers for classifying protocol type or version. So we don't need a detailed prompt here. And the prompts in the blue background are what we are using in practice. We pass the global call graph and ask, show where messages from the remote are received and where they are processed. So as the agent walks through the global call graph, it indexes and reviews each function's pseudocode, marks potential receive and parse functions, and returns the result in JSON format. The previous step also aims to reduce the search space. It cuts related branches and keeps the pipeline focused on the path. And here's the core step, data structure reconstruction. The goal is to know every buffer size before any memory access. If we get this wrong, we will miss all the bugs or get tons of false positives. First, we need to find every allocation set, like malloc, calloc, or a class constructor. Our IDA plugin takes each set and stores the decompiled function to the database. It also parses the AST at the allocation site to build an initial data structure layout based on how the code initializes the fields, like the code name on the right. Then the data structure analyzer agent scans the code base with its functions that satisfy the policy, like match the field type, name of site, or by a relevant function or class name. So aside from the policy and AST parsing routines, the rest is done by the agent. It adds missing fields, infers types, renames members, and text-controlled fields. So by the time the vulnerability analysis agent starts, the reconstructed structures are expected to be as complete as if we had the definitions in the source code. And next, I will show how this works on a concrete example. Take the C Transport Manager class from CVE 2024-34587 as an example. In the constructor, this pointer represents the object. So every read to an offset becomes a candidate field. For example, the offsets hex 303 and hex 1072. They are later normalized to hex 978 and hex 2180 based on the tab. And furthermore, the agent renames the hex 978 to PC Samsung BT buffer because of the cast in the code. Now look at the C Transport Manager start receive. This is the packet receive function, and I picked some of its colleagues on the right. The first function, the PSI memFreeX, it is not a member function, and it doesn't touch any fields of this pointer. So the agent just dropped it. In the next function, start RTCP send, it is a member function that matches the class name rule. And inside it, we see new accesses. So the agent will add 2 fields to C Transport Manager class. And for the offset hex 2310, the agent follows the return value of PSI create event X. The inverse its name is event handle. Next, the function RTP create. The agent follows this function because it return value points to C transport manager. So guided by our prompt, the agent thinks this would help to complete related data structure. Assumed unknown quality struct is unknown 1, and based on the return offsets, the agent adds 3 fields and infers the name of the first field. And this explains how the data structure's relation map grows step by step. And then in the last case, the function create buffer, it takes this plus 303 as the argument, which satisfies offset match policy. And inside this function, create buffer, the argument is treated as the class, this pointer. So if the offsets 5 and 14 are not in the layout yet, the agent will add them and infer their names. So to summarize, the data structure analyzer agent first completes the missing fields of C transport manager that are accessed outside its constructor. It then infers and fills in related data structures that may contain pointers to C transport manager. And finally, it completes a subclass that is referenced by a field within C transport manager. So once all of these necessary data structures are ready, the vulnerability analysis agent begins at the packet receive functions, then follows the data into each parse function, like the taint analysis from the source to the sink. The agent enters every function with the value ranges, buffer sizes, and any necessary constraints. So look at the agent exactly needs a prompt template, the code context, and a bug model. The code context includes the argument list, types, reconstruct data structures, and which fields are attacker controlled. And this info acts as the preconditions, like what I mentioned before. So with this, the large language model can tell if the code is vulnerable or not, and explain why. Like human experts, after knowing what specific variables and their potential values, then give a code snippet, it is easy to spot the vulnerabilities. And during the development, we met a problem. We saw everything in the JSON format, but the large language models didn't always return the valid JSON strings. They would drop the codes or failed to escape characters on the first try. So our fix is feed both the error report and the bad JSON strings back to the model. And on a second run, the large language model usually fixes the problem itself. Reasoning models do this job well, but they are too slow and costly. And lighter models are less accurate, but good enough for the format repair task. The accuracy is 90% or 95%, doesn't matter. So we built a model router, send heavy tasks to OpenAI O3 or DeepSeek R1, and send the light tasks, like the fixed JSON strings, to O4 Mini or V3. So when the run is finished, the pipeline finally hands over what we have been waiting for. The report shows how many vulnerabilities it found, a confidence score, and for each case, and a clear description of this bug. And we also include logs of reasoning history, so we can triage the bugs quickly. So now let's apply the pipeline to the real-world target, starting with a simple bug pattern. And here's the bug pattern. It's very simple. An index goes beyond the buffer, and in the demo, it is the V1 grows beyond the sizes of buffer A and buffer B. So reads and writes go out of bounds. To make the agent focus on this case, we give it a short prompt to describe this exact pattern. And here's the first bug it found, the SVE 2024-1490. The green blocks are the buffer that gets corrupted, and the red blocks indicates the bad index. And code on the right is the raw data structure reconstructed by the agent. Matching colors means those fields are the same. And the text lower right is what BinWhisper reports. And as the human expert, after analyzing this bug, I summarize the root cause. So each time entering this function, the counter at v13 of at 0 increases by 1, but the written buffers are allocated at small sizes and is fixed. So when the counter grows past to those sizes, out-of-bound writes are generated. And this is what the agent exactly said. So this function contains an out-of-bound write, and the processing loop increments the packet count without the bounds check. And its triggering condition is by crafting a packet with multiple NAL units. And bug 2 is the same pattern. An unchecked counter keeps increasing when re-entering this function and eventually overflow this buffer. And bug 3 to 5 shares the same root cause, so I will skip the repeats and go to the benchmarks. And I have to say that such bug patterns might be the simplest you have ever seen in Black Hat, and I guess why the large language models can find them. And we tested different models for vendors. First, cost matters to both the independent researchers like us and to big teams. Only considering the token price, the OpenAI 4 Mini, Cloud 3, DeepSeek R1, and 7 Plus are the best deals. But the bugs detection and confidence are the key metrics. The calculation of confidence is also delegated to the large language model itself, based on the uncertain variables number and missing code context. Checkmark in the bugs row means all the reported bugs were found, but confidence may differ. In our experiments, the O3 from OpenAI was the most stable one. It found all the bugs with high confidence in our runs, and O4 Mini and the DeepSeek R1 did well, but sometimes missed a few bugs during the testing. And as you can see, any cases with a confidence score less than or equal to 80% will be dropped. This is because after our verification, reported cases with higher confidence were all confirmed as the true positives. However, things get worse below that threshold. Massive numbers of false positives start to mix in with the results. And finally, O3 and O4 Mini finish in a reasonable time window, but DeepSeek R1 takes much longer, up to 21 hours on the same job. And here's our takeaways. So first, this is not a rigorous academic study, and we are not here to prove or define assesses. Instead, our work provides a practical evidence that large language models play an important role in our tool for discovering the real-world vulnerabilities in 0 days. We believe this direction will become a trend. And next, a recent concern is, will large language models replace security researchers? My answer is no, and on the contrary, they take the boring parts, and we get much more efficient than before. And the last one, yes, the tool is still reporting new bugs, and I have to look at some tonight. OK, thank you for listening. I hope this was helpful, and I will upload it to the website for anyone who is interested to refer to. Thank you.